Edge and trim failures are among the most common complaint categories in automotive coatings, yet they are often misunderstood. Customers notice peeling, chipping, or corrosion along panel edges, hem flanges, and trim interfaces and assume the coating is defective. From an OEM perspective, these failures are highly predictable because edges concentrate mechanical, chemical, and thermal stress, creating conditions where coatings are most likely to fail first. Edges are geometrically complex and often have reduced film build compared to flat surfaces. Spray patterns deposit less material on tight radii, leading to thinner clear coat and base coat coverage. Even small deviations in application can create high-stress zones. Thin films have lower resistance to mechanical stress, chemical penetration, and UV degradation, making them the weakest points in any coating system. Trim interfaces add additional complexity. Adhesive tapes, rubber seals, plastic trims, and molding attachments introduce differential movement and abrasion points. Every time a vehicle flexes, vibrates, or is exposed to thermal cycling, these areas experience localized strain far higher than on flat panels. Repeated low-level stress can lead to microcracking, crazing, and eventually delamination. Cure balance and crosslink density again play a central role. High crosslink clear coats resist chemical and UV attack, but have reduced elongation capacity, making them brittle over edges. Low crosslink formulations are more flexible, but can be penetrated more easily by water, chemicals, or road contaminants. OEMs must optimize crosslink density to allow sufficient strain absorption without compromising long-term protection. Residual stress from curing is amplified along edges. During polymerization and bake, the coating shrinks toward the substrate, creating tensile stress at corners. If primer and base coat layers are too thin or improperly cured, stress is not evenly distributed, and the coating is preloaded with latent failure points. Thermal cycling and mechanical flexing accelerate crack initiation in these regions. Edge failures are also exacerbated by environmental exposure. Water ingress, road salts, and industrial fallout preferentially accumulate in corners and hem flanges. Thin or stress coatings allow rapid diffusion into the substrate, promoting localized corrosion beneath the coating. This is why corrosion creep often originates at edges, even when flat surfaces remain intact for years. Additives can influence performance, but cannot fully compensate for poor coverage or mechanical stress. Slip and flow additives help the coating spread more evenly, improving edge coverage slightly. Flexibilizers in primers and clear coats increase elongation capacity at edges. Internal stress relief additives reduce residual shrinkage. However, none of these compensate for inadequate film build, poor spray technique, or design-induced stress concentrations. Substrate choice and geometry significantly affect edge performance. Aluminum edges expand faster than steel, increasing thermal strain. Welded or folded edges introduce stress risers. OEM validation programs test worst-case geometries to ensure coatings maintain integrity under combined thermal, mechanical, and chemical stress. Any shortcuts in application or layer consistency can be catastrophic. Detection of edge and trim failures requires both visual inspection and targeted stress testing. Chipping, delamination, microcracking, and early corrosion are observed under accelerated environmental simulations, including thermal cycling, humidity exposure, and simulated mechanical abrasion. Patterns of failure often indicate whether the root cause is mechanical, chemical, or process-related. From a troubleshooting perspective, OEM engineers first assess film build, application consistency, curing profiles, and additive distribution. Edge and trim failures are rarely due to a single layer. They are the result of compounded factors across the primer, base coat, and clear coat stack. Adjusting one layer without considering the others often shifts the failure point rather than eliminating it. Edge and trim stress failures illustrate the principle that coatings are dynamic, multi-layered systems that interact with substrate geometry, thermal cycles, mechanical movement, and environmental exposure. Optimizing coverage, crosslink density, curing, and additive strategy for these worst-case areas ensures that the coating survives its intended life while maintaining appearance and corrosion protection. if you've observed chipping, cracking, or corrosion along panel edges or trim interfaces. Leave your questions in the comments. We'll continue analyzing mechanical and environmental failure modes with OEM-level insights in the upcoming episodes.